Okay, so let's have a look at the 2015 Phys 1001 exam paper. Um, Alright, I've got my short off here. Okay, so formula sheet this year, 2017, the formula sheet is actually in a separate booklet so that you can have handy access to it. So alright, let's have a look at these questions and do what we can. A small circular puck collides elastically with a large circular puck initially stationary on a frictionless level surface. After the collision, which one of the following is true? The small puck has the same speed as before but in a different direction. No, that can't be true. If it had the same speed, it would have the same energy, but the big puck would be moving as well, so you'd have more energy than you started with. The small puck is moving faster than before. Absolutely, definitely that can't be true. The small puck is moving slower than before. Well, that seems highly likely, given that some of the energy has been transferred to the big puck. You would think that the small puck would be moving slower than before. So I'm going to go with C. Let's have a look at these others. D. The large puck is moving with a speed depending on the mass ratio and in the same direction as the initial velocity of the smaller puck. There's nothing to say it's moving in the same direction. It could have been a glancing collision to move off to the side, so that's not true. The pucks will stick together in order that energy be conserved. No, we know that that's an inelastic collision where they stick together and energy is always lost. Okay. A ball of mass m is a uniform sphere of radius r. It rolls down an incline without slipping. Initially at rest at a height h, it exits onto a smooth level surface. The moment of inertia is 2/5 mr squared. What will its centre of mass speed be at the bottom? Okay, well, we know that normally if you just don't worry about rotational kinetic energy, you know that the loss of potential energy, mgh, is going to be equal to 1/2 mv squared, and you can rearrange that to get v equals the square root of 2gh. Okay, so that's an upper limit on how fast it can be going, because this is the speed it would be going if none of that lost potential energy was turned into rotational kinetic energy. So we know that it can't be D, but all the rest unfortunately look promising. So because they're all less than, that looks a bit small, but hey, I suppose there's probably no, just have to do a calculation. Okay, so here's our ball, it's rolling, and we know that it's got an angular speed omega, and we know its linear speed v equals omega r for a rolling ball. Okay, so therefore the loss of potential energy, mgh, is equal to the kinetic energy of the centre of mass plus the rotational kinetic energy. So v equals omega r, so omega equals v on r. Okay, so this is 1/2 mv squared plus 1/2 times I, which is 2/5 mr squared, times omega squared, which is v squared over r squared. R squareds cancel out. 1/2 and 2/5 is 1/5. So we get 1/2 plus 1/5, which is, so we get 1/2 plus 1/5 times mv squared, and that's 7/10 mv squared. So mgh, m's cancel out, v squared equals 10/7 gh, so v is the square root of 10/7 gh. Okay, see. Fun. A block of mass m slides down a frictionless incline. Initially at rest at a height h, it exits onto a smooth level surface with a coefficient of kinetic friction mu. The block comes to stop after a distance x, which must equal. Okay, these ones are actually quite easy because the work done by friction is equal to the frictional force, which is mu mg on the horizontal surface, times the distance it travels, x, alright? But that work that's done is the same as the distance it falls. Okay, so it comes down a distance h. So the m and the g cancel, and we simply have mu x equals h, so x equals h over mu. And at this time, I'm always grateful to see that, yes, that is one of the answers that's present. Okay, so this here, work done is equal to the force, which is friction, times the distance it travelled. And that work done takes away all of the kinetic energy that it got from the potential energy mgh. Okay. Now, the wheel is formed from a metal ring of mass 1 kilogram and radius 20 centimeters held in place by spokes of negligible mass. It's free to rotate about its center. With the wheel initially at rest, a force of 10 newtons is applied constantly and tangentially to the rim for 10 seconds. In the absence of friction, other force, what final angular speed? Okay, so this is just, for linear motion it's F equals ma. For angular motion, its torque is equal to moment of inertia times angular acceleration. But these are the same, hundreds of years of physics. We thought we'll make them look the same so they're easy to remember. Okay, so therefore in this case our torque is equal to 10 newtons times the distance, which is 0.2, which is 2 Newton meter. That's our torque. Our moment of inertia, I, is equal to mr squared. Why is it equal to mr squared? Because all the mass is at a distance of 20 centimeters from the center, and that's the moment of inertia for any mass at a distance r from the axis, is mr squared. So this is equal to, what's it? So it's equal to 1 kilogram times 0.2 squared, which is 0.04, whatever units it is. So that allows us to work out our angular acceleration. Angular acceleration alpha is equal to torque over I, which is equal to 2 newtons times meters divided by 0.04. Whoa, that is a big number. That is, I'm going to get a calculator now. I should have had one to start with. Oh, it works. 2 divide 0.04 equals 50. Whoa, 50 radians per second squared. So it says it's going to be applied for 10 seconds. So the final angular velocity omega is equal to alpha times t, same as v equals a times t. Okay, so therefore this is equal to 50 times 10, which is 500 radians per second. Whoa, lots. Luckily that answer is there. I assume it's correct. And now we come to the last of the mechanics question from the 2015 exam. And an object is dropped from the top of a tall building. It falls under gravity with linear air drag such that its vertical speed is given by v of t equals v tau times 1 minus e to the minus t over tau. Okay, if you look at this equation, alright, it tells you, it says that the as t gets bigger, this term gets smaller and smaller, so its limiting speed is g times tau, right? That's its limiting speed or terminal velocity. But anyway, okay, object hits the ground after 1.7 seconds with a speed equal to half its terminal speed. The terminal speed is, okay, so as I said, the terminal speed is just g times tau, because this term here will go to 0 for large t. So therefore we can say that a half g tau, that's a half the terminal velocity, is equal to g tau times 1 minus e to the minus 1.7 over tau. Okay, so clearly from that we need that e to the minus 1.7 over tau is equal to a half, and so therefore minus 1.7 over tau is equal to the natural log of a half, taking natural logs of both sides of that. If you didn't like that, it's okay. You can just work backwards from the answers. But I'm going to use that. So I'm going to say that therefore tau is equal to, so put that up there, put that down there, minus 1.7 over log, natural log of a half. So strange calculator, minus 1.7 divide natural log 0.5 equals 2.45. Okay, so therefore its terminal speed should be tau times g. So if I times that by 9.8, I should get 24. There it is, 24. Beautiful. Okay. Yeah, that's fine. That's the end of the mechanics section, so I'll stop there. I'll do the other section.